Hi everyone, I'm back with another walkthrough. Today we will be going over Physics Paper 1 and it's the Combined Science Trilogy Higher Paper and it's a 2019 paper. Question 1. A student investigated how the current in a resistor varies with the potential difference across the resistor. Figure 1 shows part of the circuit used. The student connected an ammeter and a voltmeter into the circuit. What is the correct way to connect the ammeter and the voltmeter into the circuit? So you should all know that the ammeter is always connected in series, a voltmeter is always connected in parallel. And we are connecting an ammeter and a voltmeter to a circuit that has a resistor. So let's have a look at, so we're looking at ammeter in series, so we know that's out, and we're looking at voltmeter in parallel, so we know it can't be that one, it can't be that one. So we're left with two options here. So let's have a look at this one. In series with the resistor, yes, sounds about right. In parallel with the resistor, yes. The reason why we don't go for the last one is because this option here says in parallel with the cell, but we want in parallel with the resistor. Question 1.2, the student increased the resistance of the variable resistor. So we're increasing the resistance. How did increasing the resistance affect the current in the circuit? If you increase the resistance, what you're doing is you're making it very difficult for the electrons to travel through the wire, which is basically your charge, your current. So that means the current would decrease. Question 1.3, how should the student change the circuit to give negative values for current and potential difference? So let's just say right now the student has positive values. How do I get negative values on the actual meters? So if you think back to practicals that you've done in your lesson, if you think back, you should know that what you do is you swap the wires around. So the way you would phrase that is you would say reverse the connections to the cell, which basically means swap the wires. But if you say swap the wires, you won't get a mark. So stick to these words. Name the type of relationship between current and potential difference. If you think back to your practicals and the work that you've done in your lessons, if I have potential difference here, current there, your graph would be a straight line. Okay, and it's a line that goes through zero. So this relationship is called directly proportional. When one variable increases, the other variable increases too. Write the equation which links current, potential difference and resistance. So this year you are very lucky. You will be given an equation sheet which looks like that. Okay, and it will say for use in June 2024. So we have a look at an equation that has these three variables. So I'm looking for potential difference, I'm looking for current, I'm looking for resistance. So you can either write out the word equation or write out the symbol equation. Best is to write out the symbol equation because it's easier and you know you would get the mark. So the equation is V equal I times R. These are easy marks, so take your time, select the correct equation from the equation sheet. Okay, the current in the resistor is 0.12 amps and the potential difference is 3 volts. I'm happy with my unit, calculate the resistance. So my voltage is 3, my current is 0.12, I'm working out my resistance. I can see that I need to rearrange. If I put those numbers into my calculator, I should get 25. Transfer that number across here. It's 25 ohms. Question 2.1. A scientist cooled the air inside a container. The temperature of the air changed from 20 to 0. The volume of the container of air stayed the same. Explain how the motion of air molecules caused the pressure in the container to change as the temperature decreased. This topic is your P3. Okay, so this is where you're looking at particle model of matter. So here, the first thing you would say is if the temperature decreases, pressure decreases. So the pressure decreased. Second bullet point, because, so look here, we're going from 20 to 0. So the pressure has decreased because molecules have less kinetic energy. If particles have less kinetic energy, that means that there will be fewer collisions. So fewer collisions. So this is always the case when the temperature drops. Okay, so that's 3 marks, 3 bullet points. That's your answer. 2.2. The air contained water that froze at 0. The change in internal energy of the water as it froze was 0.70 kilojoules. The specific latent heat of fusion of water is 330 kilojoules per kilograms. Calculate the mass of ice produced. Use the physics equation sheet. So your physics equation sheet, if we take a look at that, you can see it's this equation here. Thermal energy for a change of state, mass times specific latent heat. Okay, so let's take you back. Now the first thing you need to check is, are you happy with the units? Normally, if you have kilojoules, you would convert to joules. Okay, now if you have a look here, energy is kilojoules. Specific latent heat of fusion is also kilojoules per kilogram, so I'm happy with that. And the final mass will be in kilograms. So because these both are in kilojoules, it's not necessary for me to convert. So let's have a look. So your first step is always write out the equation. So change in energy, mass multiplied by specific latent heat of fusion. So change in energy, where are we? It's 0.7. Mass is what I'm trying to work out. My specific latent heat of fusion, it's there. 330, rearrange, 0.7 over 330 should give me the mass, which is, let's have a quick look, 0.70, divide that by 330, my answer is 0.0021, transfer that onto the final space there, and that should get you 3 marks. The air also contained oxygen, nitrogen, and carbon dioxide. Oxygen boils at -183 degrees Celsius and freezes at -218. Nitrogen boils at -195, freezes at so and so. Right, so I'll come back to that. Let's just start off with oxygen. So the best way to answer these kind of questions is to kind of draw like a number line, right? So oxygen, I've got -183. I've got, so boils there, -218 would be there. And we are looking at what happens at -190. So -190 would sit there. So at -218, it's a solid. Yeah. and at minus 183 it's boiling, which means it's a gas, it becomes a gas there. So if minus 90 is in between those two values, then if I'm boiling it here, that means that minus 90 it should be a liquid. So go to the top, tick liquid. Let's do the same for nitrogen. So nitrogen boils at minus 195, freezes at minus 210, and I'm trying to work out what it is at minus 90. So minus 210, it's a solid. It boils at minus 195, so it's a solid. It's a liquid somewhere here, and then it's boiling now. It's boiled at minus 90. It should be a gas. So you tick gas. Carbon dioxide, it says sublimates, and sublimation is when a gas misses out the liquid state and becomes a solid. So carbon dioxide sublimates at minus 78 degrees Celsius. Okay, so, or solid to gas or gas to solid. So carbon dioxide sublimates at minus 780. The scientists continue to cool the air to temperature. Okay, so minus 90. So there's minus 90. There's minus 78 degrees Celsius. So gas here, and then to minus 90 it should become a solid. So you tick solid there. So a question like this, it really helps for you to just draw out number lines, put numbers in. Even I do it all the time, just to kind of make sure that I'm on the right track and I select the correct state. Right, next question. 2.4, the air also contained a small amount of argon. As the temperature of the air decreased from 20 to minus 90, the argon changed from a gas to a liquid to a solid. Explain the changes in the arrangement and movement of the particles of the argon as the temperature of the air decreased. So we're looking at arrangement of the particles and movement of the particles at each state. Okay? So let's have a look at gas to a liquid first. And we can say that here particles change from being spread out to touching each other. And particles will change direction. Because they're coming closer together. So you can also, because gas to liquid, that's cooling, you can also say that as the argon cools, the particles will slow down. Remember, in a gas state, the particles are moving faster. When the particles come closer together in a liquid, there's hardly any kinetic energy because the particles are close together. So as argon cools, the particles slow down. And you can also say, because the particles are coming closer together, you can say the density increases. And then we repeat for liquid to a gas. For a 6 marker, you are allowed to have subheadings. You can have bullet points. So liquid to a solid, I should say. So liquid to a solid, particles change from a random or irregular arrangement to a regular pattern. Because remember, it's becoming a solid. You can also add that particles change from moving freely to fixed positions. And go back to the question, it does say talk about arrangement and talk about movement. So I would say for each bullet, for each section, make sure you've done that. Have you talked about arrangement? Yes. Yep. Have I talked about movement? Yep. Slowing down, moving freely to fixed positions. Okay. Here you can also say liquid to a gas, the energy is decreasing. And then you can finally you can say attractive forces between the particles in a solid are a lot stronger than in a liquid. So attractive forces in a solid are stronger than in a liquid. And that should be enough. Question 3, a hybrid car has an electric motor and a petrol engine. Petrol is a non-renewable energy resource. What is meant by a non-renewable energy resource? So you can here say it's an energy resource that cannot be replenished as it's used, or you can say an energy resource that will run out. An energy resource that will run out. Right, the electric motor in the car is powered by a battery. To charge the battery, the car is plugged into the main supply at 230 volts. The power used to charge the battery is 6.9 kilowatts. Calculate the current used to charge the battery. So if you have a look at your equation sheet, you need to find the equation that has power, potential difference and current. And if you have a look, it's this one here. P equals V times I. Your first step is write out the equation. Then have a look. That's volts. Look at the units. That's kilowatts. So I need to convert 6.9 kilowatts to watts. You cannot be using kilowatts. So multiply that by 1,000 to get watts. So remember that. To go from kilowatts to watts, multiply by 1,000. That should get me 6900 watts. Right. Power is 6900 watts. My voltage is 230. I am calculating the current. Rearrange the equation. Whack those numbers into your calculator. You should get 30 amps. Explain the difference between direct and alternating potential difference. Right, so 2 marks. So here you would say, so I'm just using a bit of shorthand just to speed things up, but you would write the whole thing down. So direct, alternating potential difference is always in the same direction. So if you think back to the graph, you should see a straight line. Okay, that's your 0. straight line for DC, alternating potential difference changes direction. So here you have negative and positive values, and a graph for that looks like this. Okay, 3.4, the cable used to connect the car to the mains electricity supply has a low resistance. Explain why it is better to use a cable with a low resistance than to use a cable with a high resistance. So here you need to say that a lower potential difference across the cable, that's what we end up with. And then also it is more efficient. So it says explain why it is better to use a cable with a low resistance. If you've got low resistance, then you've got lower potential difference across the cable and it's more efficient, or you can even say here it won't get as hot. Or you can also say the car battery can charge faster, but that's how simple the answer is. Right, next question. Student, okay, built the following circuit. The lamp has a resistance of 10 ohms. Okay, so the circuit is series, but the resistors are in parallel. Each resistor has a resistance of 10 ohms, 10. What is the total resistance of the circuit? Right, so there's two things you need to remember here. There's two rules. So, in a series circuit, okay, now let me just rephrase that. If you have two resistors in parallel, let's just say this is 5 ohms and that's 5 ohms, to work out the total resistance, you add those two values up, which will be 10 ohms. That's if resistors are placed in series. Now here, the resistors are in parallel. So in parallel, there's no calculations involved. What you need to do is have a look at the two numbers, pick which one is lowest. Well, in this case, it's 10 and 10. And then you would say, in a parallel, when resistors are placed in parallel, the total resistance would be less than the lowest value. Now, the value here is 10, so you would say it's less than 10 ohms. Okay, so all of this together is less than 10 ohms. But the question is, what is the total resistance of the circuit? Then we go back, we worked out the overall resistance here, and now let's go back to the entire circuit. Now that's 10 ohms, and then we said that's less than 10. So 10 plus 10 is 20, but we said less than, so has to be less than 20. So let's have a look. Can't be that one. Nope, nope, less than 20 ohms. Okay, now how would you explain that? So for the explanation is basically what I've just said. So you need to say the resistance or you can say that the resistance in a series add up. So the resistance, yeah, I think that's an easier option. The resistance in series adds up, and then for this bit here, second mark, you need to say resistors in parallel. Apologies, can't spell today. Resistors in parallel have a smaller resistance than the lowest value resistor. Then the lowest value resistor. Okay, so these are two rules you need to remember. So just to recap in a series circuit, so when resistors are placed in series, add up the resistance in a parallel, pick the lowest value resistor, and then you say less than whatever that value is. Okay? Right, 4.3. Draw a circuit symbol for a thermistor. So a thermistor is a type of resistor. All resistors have a rectangle. Okay? Now this is the component where students confuse the symbol with a variable resistor. A variable resistor has an arrow. This one doesn't. A horizontal line, diagonal line like that. That's a thermistor. The student increased the temperature of the thermistor. Explain how the current in the thermistor changed. The current, so if you increase the temperature, the current increases. And then it's an explain question. Explain question always means why. The resistance decreased. The current increases because the resistance decreased. Figure 3 shows another circuit the student built. Explain how the potential difference across the resistor and the lamp will change when the switch is closed. So for the resistor, so these are 4 marks. We need 2 bullet points for the resistor, 2 bullet points for the lamp. So the PD, the potential difference across the resistor, becomes 0 volts. Explain question, tell me why. So the second bullet point you would say because so it's this bit here that we're looking at, because there is a short circuit across the resistor. And then for the lamp, you would say the potential difference across the lamp increases. Why? Because the current increases. Question 4.5. A student investigated how the mass of water in an electric kettle affected the time taken for the water to reach boiling point. The kettle switched off when the water reached boiling point. Figure 4 shows the kettle. The heating element of the kettle was connected to the main supply. Explain why the temperature of the heating element increased. So 2 marks, 2 bullet points. The electrons, so you can say the electrons collide with particles in the heating element, or you can say there is a current. Same thing, there is a current in the heating element. Let's just go for that actually. There is a current in the heating element, which is this bit. It's explain question, the why bit. Here you can, okay, so if there's a current, then you can say which increases the energy of the particles, or you can say the particles vibrate more rapidly. Give one variable that the student should have controlled. So here it should be the starting temperature of the water. The starting temperature of water. Figure 5 shows how the mass of water in the kettle increased. Water in the kettle affected the time taken for the kettle to switch off. Suggest why the line on figure 5 does not go through the origin. So we're looking at why don't we have the line starting at 0. So here, think about it. It's going to take time to heat the water up. So it won't start off at 0. So the kettle took time to heat up the water. Suggest why the results give a non-linear pattern. So here you would say the energy transferred to the surroundings changes as the mass of water changes. So remember, there's always heat dissipated to the surroundings. So the rate, or just energy, the rate of energy transfer to the surroundings changes as the mass of water changes. Question 5.5 is a calculation question. It's a 6-mark question. It's a multi-step calculation question. So let's have a look. The power of the kettle was 2.6 kilowatts. The kettle took 120 seconds to heat 0.8 kg of water from 18 to 100. Calculate the specific heat capacity of water using this information. Give your answer to 2 significant figures. Right, I've got power and then I've got time. So let's start off by writing out the equation for specific heat capacity. And again, that's on your equation sheet. So it is the 4th one down. It'll be this one. Okay, so I'm going to write the shorthand version of the equation. So energy change equals mass times specific heat capacity times temperature change. So I've got mass. I'm working out specific heat capacity, which is C. That's my M. Temperature change is there. So I'm missing energy, which means I've got power there and I've got time there. So there must be another equation which allows me to work out energy. So let's have a look at that one. So they've given me power, they've given me time. So it's energy transferred over time gives me power. Okay, so power is energy transferred over time. So power is in kilowatts. So 2.6, multiply that by 1,000 to get power in watts. Okay, so go back here, 2,600, working out energy. Time is 120 seconds there. Rearrange, I get 2600 times 120. That gives me the energy transferred. That is 312000. Right, so that's sorted. Now I've got my energy transferred. So let's substitute all these values into that equation. So 31200, mass 0.8 kilograms. Specific heat capacity is what I'm working out. So leave that as C. Right, temperature change, the difference between the two, so 100 minus 18 gives me 82 degrees Celsius. Bring that down. So 312,000, 0.8 times 82 gives me 65.6 times C. Rearrange, divide. I get my C, which is 4756 joules per kilogram. Now, go to the last step here. It says give your answer to two significant figures. So that must be to two significant figures. So have a look at the third digit. It's 5. Add 1 to 7, 4800. That's your answer. Right, next question. Lanthanum is a radioactive isotope. A nucleus of lanthanum 114, the number that you see after the dash is the mass number, emits gamma. So what do we know about gamma radiation? Well, it's part of the electromagnetic spectrum. It's a wave, which means it has no mass, no charge. What happens to the mass number and the charge of the nucleus when gamma radiation is emitted? So it has no charge, it has no mass, which means that it won't change the mass or the charge of the radioactive isotope. So we're looking at stays the same, stays the same, stays the same. Why is it difficult to detect gamma radiation? So two possible things you can say. You can either say gamma radiation is very penetrating, or you can say it's weakly ionizing. That's the answer. So the reason why it's difficult to detect is because gamma radiation is very penetrating. Right. Activity is the rate at which a radioactive source decays. A teacher measured the count rate from a sample of lanthanum using a Geiger-Müller tube. So a tube that detects radiation. Explain why the count rate was less than the activity of the sample of lanthanum. So here you talk about radiation spreads in all directions. Spreads out in all directions, and only some of the radiation goes into the GM tube. So this question is quite a challenging question as we get closer towards the end. The teacher investigated how the thickness of lead affected the amount of gamma radiation that could pass through it. Figure 6 shows the apparatus. There's my sample, there's my lead, there's my GM tube, which obviously counts up the activity. Explain why the teacher stood as far away from the apparatus as possible to reduce the amount of radiation received. So to reduce the amount of radiation received, and the second marking point is to say that radiation increases the risk of cancer, which is why she stood far away from the apparatus as possible. Table 1 shows the results. The teacher concluded that the count rate was not inversely proportional to the thickness of lead. So inversely proportional means your thickness, you're changing that, so that's on the x-axis. The count rate would go there. So as you increase the thickness, the count rate in counts per second decreases. So inversely relationship, the graph would look like that. Explain why the teacher was correct. So if you have a quick look, you can see that as I'm increasing the thickness, yep, my count rate is decreasing. Let's have a look. Yeah, okay. So explain why the teacher was correct. So the teacher's saying it's not inversely proportional. Well, the first step is work out the product of thickness and count rate. So multiply these two numbers, okay? So let's do the first one. 0.5 times 110 should give you 55. Do another one. Let's go for 1.0 times 60 gives me 60. If you do two calculations, you get 2 marks. And then the third mark is to say is a comparison of the calculated values and a recognition that they are different. Because as a thickness, so if you look at the graph, they should be more or less the same as you come towards these values of thickness of lead. But that's not the case. If I keep going, 1.5 times 33 should give me 50. 2.0 times 18 should give me 36, and then 2.5 times 10 should give me 25. So then these numbers here should be more or less similar, but they're not. So which is why the teacher's correct. It's not inversely proportional. Your third mark is just to kind of explain that the values are different for 1.5, 2 and 2.5, because it was, like I said, if it was inversely proportional, these values here will be more or less the same, but they're not. Lanthanum 140 can also emit beta radiation and change into cerium. Complete the equation showing the decay of lanthanum into cerium. So basically, the decay is forming a new element. Just a quick recap, in the nucleus of an atom, you have protons and neutrons, yeah? So in the center, you've got your protons and neutrons. Beta decay is when a neutron becomes a proton and an electron, a fast moving electron. This leaves the nucleus. The proton stays in the nucleus. Nucleus has a charge of 1. So if a neutron splits into a proton and an electron, a proton also has a charge of 1, which means that the mass of the nucleus doesn't change. Okay? It's the electron that leaves. So the atomic number I've added an extra proton into the nucleus. So the atomic number, which is basically the proton number, should change. It should go up by 1. So one more time, a neutron splits into a proton and an electron. Electron leaves the nucleus. That's your fast moving electron. Proton stays. I've added an extra proton. So say for example, initially I had 3 protons here. Neutron splits. I've now made a new proton particle. I've now ended up with 4 protons. If you change the proton number, you've made a new element. Okay, so let's have a look. This is my new element. The mass of an electron is 0. And the lower number here is -1. So let's have a look. So remember I said to you the mass won't change. Overall, the mass number won't change because the neutron had a mass of 1. That's gone now because it's split and it's been replaced by a proton, which also has a mass of 1. So the mass number should stay the same here, 140. Okay? The proton number should go up by 1. So initially it was 57, it should go up by 58. If you find that quite a difficult concept to understand, there is an easier way. What you need to do is add these two numbers up. It should take you back to the original mass number of the original element. So 0 plus 140 is 140, okay, correct. 58 minus 1 takes you back to 57, so you can always check your calculations that way, okay. So you need to be familiar with writing out decay equations. This is beta decay. You need to also be able to write out equations for alpha decay. So make sure you have a look at that. Okay, so this is the most challenging question. There are other isotopes of cerium which are radioactive. Different isotopes of cerium have different half-lives. The half-life of an isotope can be found by studying how the number of atoms change over time. Figure 7 shows how the number of atoms of cerium-148 in a 120 gram sample changes over time. Right, determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared with when the sample was 350 seconds old. Right, so let me show you how you work out the half-life from a graph. You look at your y-axis, so that could be mass or it might be number of atoms. So number of atoms is 5. Half of 5 is 2.5. Use a ruler, draw a line until you touch the line, the curve, go down, read that value off, and it's 50 seconds. So 1 half-life is equivalent to 50 seconds. So it takes 50 seconds for the number of atoms of cerium to decay by a half. So let's have a look. So 1 half-life is 50 seconds. If you have 2 half-lives, so if the number of atoms have decayed twice, that would be 100 seconds. 3 half-lives would be 150 seconds. 4 half-lives would be 200. 5 half-lives would be 250 seconds. 6 half-lives would be 300 seconds. And then 7 half-lives would be 350 seconds. The question says, determine the ratio of the number of cerium atoms in the sample when it's 100 seconds old. So 100 second old, I've halved it here and I halved it there. You're halving it again, half again, half again, half again, half again. So for 100 seconds, I have 2 half-lives. And then for 350 seconds, I've got 7 half-lives. 7 minus 2, because the question says compare, so you're working out the difference. So the difference between 2 is 5 half-lives. Each half-life, so halving is a half. So we're halving 5 times. So we're halving 5 times. Oops. So that should give you, so 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So the ratio is 1/32. That's your answer. Or you can have an answer of 1/32. I would prefer I personally prefer writing it that way. Okay, so that's how you would answer a question that looks like this. Determine the activity of the sample of cerium when the sample was 20 seconds old. Right, activity is number of atoms at 20 over time, change in time. So here, go to 20, it's a curve, draw a tangent. Straight line, because you will work out the gradient, yeah? So there's my tangent. Make sure you draw a right angle triangle roughly in the center of 20, yeah? Pick a square, pick a point where it'll be easier to read your value off. So if I go, let's just go here, let's go there. And do a right angled triangle there. So let's work out change in y. So that's 3. I mean, it's not 4, let's just take it as 4. So the difference there is 1, which means the number of atoms is 1 times 10 to the power of 23. Change in time, so if we just go down, have a look. So that's 10, 12, that's 16 seconds. And that's going to that point there. 20, 30, 36. So 36 take away 16 is 20. And if you put that into your calculator, that should give you 0.05 times 10 to the power of 23. That's my activity. If you do have access to the mark scheme, if you ever look at the mark scheme, you will notice the values might be different, or you might be given a range. So it does say allow a range between 4.7 to 5.9. But when you have a graph and you're working out the gradient, the examiners will look at how have you worked out the gradient, have you read the values off correctly, and if you have, you will get a mark even if the value isn't on the mark scheme. Okay, so that is your answer for that. And again, a couple of things. So 30% of your physics paper 1 is maths, and you can see why. It's because there's lots of equations. Also make sure you have a scientific calculator, a calculator that you would use in your maths lessons, a calculator that you are familiar with. Okay, if you don't have a scientific calculator, then you will struggle with questions like this, okay, where you need to be using standard form. Okay, so I hope you found that useful. So I will be uploading another video, and I believe it's the paper 2022. So that will be going up very soon too. So I hope you found that useful, and I will speak to you soon. Thank you everyone. Bye.